For today's lesson, we will be continuing the relational database model. So at the end of this discussion, you are expected to define terms, list the 5 properties of relations, be able to state 2 properties of candidate keys, define first, second, and third normal form, describe problems from emerging relations, transform ER and EER diagrams into relations. Then you should be able to create tables with entity and relational integrity constraints and be able to use normalization to convert anomalous tables to well-structured relations. So let's now go first to components of relational model. So we have the 3 components of relational model. First is the data structure, which composed of tables, also known as relations, and each table has its own rows and columns. Now we have data manipulation. It's a powerful SQL operation for retrieving and modifying data. While data integrity and mechanisms for implementing business rules that maintain integrity of manipulated data. So let's define first a relation. So basically in the discussion, we are going to use the term relation and table or entity interchangeably. So a relation is a named two-dimensional table of data. A table consists of rows or records and columns or attribute or known as field. Requirements for a table to qualify as a relation. First, it must have a unique name. Second, every attribute value must be atomic, that is not multi-valued and not composite. Then you have every row must be unique. Cannot have 2 rows with exactly the same values for all their fields. Attributes, or also known columns, in tables must have unique names. The order of columns must be irrelevant and the order of rows must be irrelevant. Note that all relations are in first normal form. Now let's go with the correspondence of ER model. Relations or tables correspond with entity types and with many-to-many relationship types. Rows corresponds with entity instances and with many-to-many relationship instances. And columns correspond to attribute. So you have to take note that the word relation in relational database is not the same as the word relationship in ER model. Now let's talk about key fields. So when you say key fields, keys are special fields that serve 2 main purposes: primary keys and foreign keys. So when you say primary keys, they are unique identifiers of the relation. Example, you have your employee number, you have your student number, social security number, and etc. For foreign keys are identifiers that enable a dependent relation on the many side of a relationship to refer to its parent relation on one side of the relationship. So basically, when you say foreign key, it is a primary key from one table that is being used by another table as part of its attribute. Okay, primary. So let's have this side by side. When you say primary key, is the unique identifier of a table or of a relation, such as student ID or employee ID. When you say foreign key, a foreign key is a primary key from one table, and that primary key is being used by another table as one of its attributes. So that's what we call the foreign key. Keys can be simple. When you say simple, it is single field or composite, meaning more than one field. Keys usually are used as indexes to speed up the response to user queries. So let's have here an example for, or an illustration for a primary key and foreign key. For the relation customer, you know that you have the primary key because it is underlined with a solid line. Okay? So the customer ID is the primary key for the customer table. Now notice in your order relation or the order table, it contains customer ID also. Now this customer ID is a foreign key of order table. Why foreign key? Originally, we know that customer ID is a primary key from the customer table. Now, since customer ID is being used in the order table, this customer ID in the order table is considered to be a foreign key of the order table. Okay. Now, in the order line, we notice that you have two primary keys. We call this the composite primary key. You have two primary keys for a certain table. Basically, you can have composite primary keys if you have an associative entity that is coming. When you say associative entity, that is converting the many-to-many relationship into an associative entity so that you can have a one-to-many relationship in the implementation. Now let's go to the different integrity constraints involved in database. You have here domain constraints, entity integrity, and action assertions. So when you say domain constraints, these are the allowable values for an attribute. When you say entity integrity, no primary key attribute may be null, meaning all primary key must have a value and all primary key fields must have data. Action assertions, this will be based from the business rules. So let's have an example for domain integrity. When you say domain integrity, these are the set of allowable values for a certain attribute. So for example, you have your customer ID. So the domain name are all the customer IDs, the description set of all possible customer IDs, and its domain or the allowable value is type character of size 5. Character of size 5, meaning up to 5 characters. So customer name, the domain or the allowable value is of type character of length or of size 5, and so on and so forth. Domain definitions enforce domain integrity constraints. Now let's go to integrity constraints. For the integrity constraints, we have this referential integrity. Referential integrity is a rule states that any foreign key value on the relation of the many side must match a primary key value in the relation of the one side. Meaning, when you say referential integrity, it is the enforcement of the primary key foreign key relationship. So if you're going to use, or if you're going to enforce referential integrity, you have to make sure that the foreign key that you are using in one table is a primary key from another table or from the reference table. So here are the description for enforcing referential integrity. You have restrict, cascade, and set the map. So, example, you are going to delete values from the database. So we have here example, we're going to to have delete command in our database, so we can use restrict, cascade, or set to null. So when you say restrict, it will not allow any deletion of records from the parent side of the related rows or from the source table. Then cascade, when you say cascade, if you delete a record from the parent row, automatically the table who is using that particular primary key as foreign key will also be the record will also be deleted from that particular table. When you say set to null, set the foreign key in the dependent side to null if deleting from the parent side. It is not allowed for weak entities. So we have here the referential integrity constraint from the example in the book. You have here the customer, so order, it has a foreign key customer ID, which references customer table. Now for the order line, which is an associative entity, its composite primary key is being referenced to order table and product table. So referential integrity constraints are drawn via arrows from dependent to parent table. So meaning from dependent to the source table. So we have here an example of SQL table definition. So we have here an example of SQL table definition. So when you define the table, you list here the different attributes and its allowable values. So for customer ID, you have the data type, number, and the length. Since customer ID is a primary key to enforce entity integrity, it should not be null. Okay, so how do you know that it's a primary key? You have here the constraint customer ID as the primary key. Now for the order table, notice that for the order table, we have customer ID as a foreign key. So when we define the order table, you set their customer ID. You include first customer ID as one of the attribute, and then you define that the customer ID is a foreign key referencing the customer table. So this is how you define a table in SQL. We will have more of excuse me, table definition in SQL when we are going to discuss SQL introduction. So let's go to transforming EER diagrams to relations. So you are going to map regular entities to relations. So simple attributes, ER attributes map directly onto the relation. Composite attributes use only their simple component attributes. Multi-valued attribute becomes a separate relation with a foreign key taken from the superior entity. So let's have an example of mapping a regular entity into a relation. So you have here the customer entity with simple attributes. So when you're going to transform this one into a relation, all you have to do is this. So have it in a table form. You need to underline customer ID because it is the primary key, and list all the different attributes. So this is how you convert entity into a relation. Now we're going to map an entity with a composite attribute into a relation. So the composite attribute here is the customer address. So in your customer address, you have customer street, city, and customer state. So to convert this one into a relation, all you have to do is to list all the simple attributes of the composite attributes. So instead of having customer address, you put here directly the customer street, customer city, customer state, and the customer postal code. So no customer address because the customer address has been broken down to simple attributes, which are the customer street, city, state, and state. Then you have here the postal code. Now let's map an entity with a multi-valued attribute. So your multi-valued attribute here is the scale. So when you say scale, you can have one or more scales. So what you're going to do is to create a separate relation and use foreign key in mapping this entity with the multi-valued attribute. So you have it here. Notice that you have the employee ID, employee name, and employee address. And we know that an employee has multiple skills. So you create another relation, which is the employee skill. You use employee ID as its foreign key or as its primary key taken from your employee and your skill as part of your skill. Here is a candidate key. That is why it is underlined. So this is a separate relation. So this is how you convert or you transform entity diagrams with an entity diagram in with a multi-valued attribute into a relation. So if it's a simple entity to be converted into relation, all you have to do is to list all the attributes and make sure that the primary key is being underlined. For the ER diagram with composite attribute, all you have to do is to list all the attributes plus the what call this one? The simple attributes derived from the composite attribute address, customer address. Then for the multi-valued attribute, you have to create a separate relation for that particular multi-valued attribute and use foreign key enforcement. So let's try now to map ER diagrams for weak entities. So when you see weak entity, it becomes a separate relation with a foreign key taken from the superior entity. Primary key composed of partial identifier of weak entity and the primary key of the identifying relation. So that is the strong entity. So we have this example, weak entity dependent. So we know that the dependent has a partial identifier dependent name. Okay, so we will be using this one as part of our relation. So when we are going to convert this, you have two relations named employee and dependent. Now, when you're going to check, you will the name here, the dependent name. Notice here, the dependent name is a composite attribute. You have the first name, middle name, and last name. So if you convert that one into a relation, you have to use the converted composite attribute to simple attribute, which is now the first name, middle initial, last name as your partial identifier. Now for the identifier of your weak entity, which is dependent, you will be using the primary key of the strong entity, which is the employee ID. Then you just have to draw an arrow from the dependent to the employee relation. So this is how a composite primary key is being developed. Now let's map binary relationships. So you have one-to-many, many-to-many, and one-to-one. For one-to-many, primary key on the one side becomes a foreign key on the many side. For many-to-many, create a new relation with the primary keys of the two entities as its primary key. So this is now the case of associative entity. Now for one-to-many, one-to-one, primary key on mandatory side becomes a foreign key on optional side. So let's have here mapping of the one-to-many relationship. So one in our ER diagram, we have the entity customer and order. So one customer can have 0 or more orders. Okay. So as you can see, if you're going to convert this ER diagram into a relation, you will have here the customer. So you have all the details for the customer. And for the order, you have order ID, order date. Notice that the primary key of customer ID becomes a foreign key in the many side of the relation. So that is why you have the customer ID is a foreign key in the order relation, which is coming from or which references from customer relation. So again, no null value in the foreign key. This is because of the mandatory minimum cardinality. So if you notice, why do we include customer ID as a foreign key from the order table when in fact in the original ER diagram there is no customer ID? The reason for that is in interpreting the ER diagram, it's automatic that the one in the many side of the relationship will have the foreign key of the entity with the mandatory one side of the relationship. That is why automatic we have this foreign key customer ID and order table. So let's go to mapping the many-to-many relationship. Sure that you are going to create an associative entity. So let's have this example. We have the many-to-many relationship between employee and course, and we have this attribute date completed for each course taken by each employee. So to convert that, what will happen? You have a 3 resulting relations. That is for the employee, for the course, and for the associative entity certificate, which is derived from this date completed attribute in the relationship between employee and course. So you have here for the employee, you have employee ID as your primary key. For the course, you have course ID as your primary key. Now this certificate is an associative entity which contains composite primary key. And that composite primary key is coming from the tables employee and course ID, which in this case is the employee ID and the course ID. Okay. Now let's map a one-to-one relationship. So in a one-to-one relationship, you have here one nurse can be assigned or is in charge of 0 or 1, exactly 1 care center. So to map that one, you have your nurse table, then you have the care center, you have your center location. So you have here the nurse in charge which refers to the nurse ID. Asa gikan si nurse in charge, kini sa nurse table, and the date assigned. Okay, so this is how you transform one-to-one relationship ER diagram into a relation. Then let's map associative entities. Identifier not assigned and identifier assigned. So when an identifier is not assigned, the default primary key of the association relation is composed of the primary keys of the two entities, as in the many-to-many relationship. For the identifier assigned, it is natural and familiar to end users. Default identifier might not be unique. So let's have this associative entity order line for the entities order and product. Okay. So to convert this or to map this into a relation, you will be having three different relations. So you have here the order table, the product table, and the order line table. So since we do not assign a primary key for the order line, the primary keys from the orders and product tables will be its identifier or its primary key. So it's a composite primary key. So if you're going, so that's for a mapping an associative entity with identifier not assigned. Now, what if an identifier is assigned to a particular associative entity? Like in this case, the associative entity is shipment, and it has its own identifier or primary key, which is shipment ID. So to convert this, all you have to do is three relations. Then you just have to make sure that you underline the primary key of the associative entity, and also to take note that customer ID and vendor ID is a foreign key for the shipment relation. Why? Because we know that the original relationship is many to many. That is, many customer can have many vendors. So we created the shipment associative entity. So automatic customer and customer is having a relationship with the vendor through shipment. That is why customer ID and vendor ID is a foreign key in your associative entity when you convert it into a relation. Now let's map ER diagrams to relations with unary relationship. So when you have one-to-many recursive foreign key in the same relation, many-to-many will result to two relations, one for the entity type, one for the associative relation in which the primary key has two attributes, both taken from the primary key of the entity. So let's have mapping of unary relation. Unary relation, that is a relationship of an entity within itself. So when you map this, you know that an employee is being managed by another employee. So when you map this, all you have to do is to create a manager, a foreign key that is the manager ID, and have it related to or connected to the employee ID, because a manager also has an employee ID. This is a recursive foreign key. For the many-to-many relationship, you have here unary many-to-many relationship. So many items has many quantity. So if you're going to map that one, you have to make sure that you have your item. It will result into two tables. You have your item and your component. So your component relation is called from the relation attribute quantity, which has the attribute quantity and the composite identifier, that is item number coming from the item table, and the component number, which is also coming from the item table. Then let's map ternary relationships. So one relation for each entity and one for the associative entity. Associative entity has foreign keys to each entity in the relationship. So this is a ternary relationship. So this associative entity is related to three different entities. Okay. So notice that you always have to remember that in an associative entity, it is in the associative entity side that all the many relationship is attached. So when you map this, you will have this relation. You have the patient, the physician, and the treatment. And then the patient treatment, which is the associative entity, will contain the primary key of patient, physician, and treatment. And you have your partial identifier, treatment date, and treatment time. So remember that the primary key must be unique. This is why treatment date and treatment time are included as composite primary key, because date and time is unique in every patient treatment. But this makes a very cumbersome key. It would be better to create a surrogate key like treatment number. So you can create treatment number instead of having P treatment date and P treatment time as your primary key. Now let's map supertype subtype relationships. So one relationship for supertype and for each subtype. Supertype attributes, including identifier and subtype discriminator, go into supertype relation. Subtype attributes go into each subtype. Primary key of supertype relation also becomes primary key of subtype relation. One-to-one relationship established between supertype and each subtype in supertype as primary table. So here, let's have the example of the employee, which is three subtypes: hourly employee, salaried employee, and consultant. So to map this, you have you have the supertype employee, and then you map the subtypes. Now you might be asking why you have here H employee number, C employee number, and S employee number. So these employee numbers are being inherited from the supertype. Recall the definition of attribute inheritance, that the attribute from the parent or from the supertype is being inherited by the subtype. So all employees has its own employee number. So you just have to define the employee number for each subtype of employee. Okay, so that's transforming ER diagram into a relation. Now let's go to database normalization. So when you say normalization, this is the first step in designing your database. You cannot do directly ER model or convert ER into a relation if you do not undergo data normalization. So when you say data normalization, this is primarily a tool to validate and improve a logical design so that it satisfies certain constraints to avoid unnecessary duplication of data. The process of decomposing relations with anomalies to produce smaller, well-structured relations. So when you say well-structured relations, it is a relation that contains minimal data redundancy. We really cannot eliminate redundancy, but we just have to control or minimize redundancy and allows users to insert, delete, and update rows without causing data inconsistencies. The goal is to avoid anomalies. What are these anomalies? Insertion, deletion, and modification anomaly. When you say insertion anomaly, adding new rows forces user to create duplicate data. When you say deletion anomaly, deleting rows may cause a loss of data that would be needed for other future rows. And modification anomaly, changing data in a row forces changes to other rows because of duplication. So as a general rule of thumb, a table should not pertain to more than one entity type. So let's have here an example. You have employee 2. Then you have employee ID, name, department name, salary, course, title, and date completed. So the question, is this a relation? Yes, because it has a unique rows and no multi-valued attributes. But what's the primary key? Composite. It's the employee ID and course title. So we have anomalies for this table. So the 3 anomalies are present in this table. Insertion. Can't enter new employee without having the employee take a class or at least empty fields of class information. Okay? Nakakay mga empty fields. It's anomaly. Deletion. If we remove employee 140, we lose information about the existence of tax accounting class. So if you're going to remove employee 140, this one, you will, or the tax accounting class will not have an employee who completed this course. So if this employee will be deleted, we cannot trace or we cannot associate this tax accounting class to an employee because we deleted the employee 140. So that's deletion anomaly. Okay, so who does tax accounting class belongs to if we have deleted the 140? So that's deletion anomaly. For modification anomaly, giving a salary increase to employee 100 forces to update multiple records. Why? You have 2 records pertaining to employee 100. So if you're going to increase the salary of employee 100, you have to make sure that you also increase the record for the second employee 100. So that's what we call modification anomaly. So when you say modification anomaly, instead of updating only one row, you need to update other rows that has the same or duplicate values so that you can have consistent data. So that's what we call modification anomaly. Why do these anomalies exist? Because there are 2 themes, entity types in this one relation. This results in data duplication and unnecessary dependency between the entities. So given that, given a form or a table that contains all the anomalies, we need to undergo normalization. Okay. So the process of normalization is this. Basically, we have we have different normal forms, but the accepted normal form is up to 3rd normal form. So given a table with multi-valued attributes, you need to convert this to 1st normal form. To convert a table with multi-valued attributes to 1st normal form, you have to remove all multi-valued attributes. Now, if there are no multi-valued attributes, then it is in the 1st normal form. But in the 1st normal form, there are still partial dependencies. So you have to remove the partial dependencies so that you can have the 2nd normal form. Now, in the second normal form, there are still transitive dependencies. So you need to remove transitive dependencies to achieve the third normal form. So you can stop until third normal form, or you can go further to Boy's code normal form. So when you say Boy's code normal form, that is removing remaining anomalies resulting from multiple candidate keys. But it's not necessary that you go to Boy's code normal form. And after that, you have fourth and fifth normal form. But in practice, we only go up to third normal form, because overly normalizing a database will also lead to difficulty in implementation. So we need to denormalize again to the lower normal form. So that is why the ideal normal form is the third normal form, in which you can implement your database. Now, since we are talking about dependencies, let us now go to functional dependencies. These functional dependencies are present when you do data normalization. So, functional dependency, the value of one attribute, that is the determinant, determines the value of another attribute. When you say candidate key, a unique identifier, one of the candidate keys will become the primary key. Example, perhaps there is both credit card number and SS number or social security number in a table. In this case, both are candidate keys. Now, each non-key field is functionally dependent on every candidate key. That is why it is called functional dependency. For first normal form, there should be no, or the qualification or requisites for a first normal, for a relation or for a table to be in the first normal form. There should be no multi-valued attributes. Every attribute value is atomic, and all relations are considered to be in first normal form. So let's try to check the illustration in the figures. So this table contains multi-valued attributes. So meaning this is not a relation and it is not in first normal form. So to convert this into normal form, you have to eliminate multi-valued attributes. So this is an example of the multi-valued attribute. So you have to eliminate, or you have to remove multi-valued attributes in order to convert this one into first normal form. How? You have to make sure that every row or every record has its own details. So from the multi-valued attribute, all you have to do is to distribute the order ID, which pertains to the product being ordered. So this is what happened. 1006, 1006 for dining table, writer's desk, and entertainment center. While 1007 to 1007 for a four-door dresser and entertainment center. So this is now in first normal form. And this is also a relation, but it is not a well-structured relation. So this is still in first normal form, and still we have anomalies in the first normal form. So we still have insertion, deletion, and update anomalies. Update is also known as the modification anomaly. Insertion. If new product is ordered for order 1007 of the existing customer data must be re-entered, causing duplication. And deletion, if we delete dining table from order 1006, we lose information concerning this item's finish price. Okay. Then for the update, changing the price of product ID 4 requires update in multiple records. So we have product ID 4, so you have two product ID 4, so you have to update multiple records in a table. So that's for the update or modification anomaly. So why do these anomalies exist? Because there are multiple themes in one relation. This results in duplication and unnecessary dependency between the entities. Now, from the first normal form, we go to second normal form. So first normal form plus every non-key attribute is fully functionally dependent on the entire primary key. So every non-key attribute must be defined by the entire key, not by only part of the key. No partial functional dependencies. So let's try to map the functional dependency. For the full dependency, we know that given the order ID and the product ID, we can determine the order quantity. When we have the partial dependency, given the order ID, we can identify order date, customer ID, customer name, and customer address. Another partial dependency is given the product ID, which we will be able to identify product description, product finish, and product standard price. For transitive dependency, we know that an order ID contains customer name and customer address. Now, this is not yet in second normal form because partial dependencies exist. So to convert this in second normal form, we have to remove partial dependencies. So in removing partial dependencies, the partial dependencies that you have identified in your functional dependency based in your first normal form, you have to create it as a separate table or a separate relation, just like this. So we have order ID. So this is the full dependency. Order ID and product ID will determine the ordered quantity. Now for the first partial dependency, you have here, this part here, you have the product. You name it as a product relation with the identifier product ID, which determines the product description, finish, and standard price. So this is it. This here. Now, for the second partial dependency, which is given the order ID, you determine the order date, customer ID, customer name, and customer address. So you put that in another separate relation. This. Okay. So for the order line, it's already in third normal form. You cannot there are no multi-valued attribute, no partial dependencies, and no transitive dependencies. For the product relation, it's already in third normal form because there is no transitive dependency. Now, we know that we are in the second normal form because we eliminated all the partial dependencies, and what remains is the transitive dependency. So when we know that an order ID can determine customer name and customer address. So to remove this transitive dependency, we have to create a separate relation for this transitive dependency. So for the third normal form, you need to make sure that you are already in the second normal form plus no transitive dependencies. Functional dependencies on non-primary key attributes. That's what we call transitive dependencies. This is called transitive because the primary key is a determinant for another attribute, which in turn is a determinant for a third attribute. Solution: non-key determinant with transitive dependencies go into a new table. Non-key determinant becomes primary key in the new table and stays as foreign key in the old table. So this is how you remove transitive dependencies. So originally we have this on order ID determines the customer name and customer address. So if we remove the transitive dependency, we now have order ID, order date, and customer ID. This becomes a foreign key, and we create another relation which is customer address. So in the final or in the third normal form, you have 5 relations. 5, yeah. You have this, 4 relations. You have this order line and product, which is already in third normal form, and this order and customer table. So that is now in third normal form. So let's try to have an overview of merging relations. So this is view integration, combining entities from multiple ER models into common relations. Issues to watch out: synonyms, 2 or more attributes with different names but the same meaning. Homonyms, attributes with the same name but different meanings. Transitive dependencies, even if relations are in third normal form prior to merging, they may not be after merging. Supertype subtype relationships may be hidden prior to merging. Then we have enterprise keys. These are primary keys that are unique in the whole database, not just in a single relation. This corresponds to the concept of an object ID in an object-oriented system. So this is an example of an enterprise key. You have object ID, object type, so on and so forth. Okay, so that's all for relational database model. So I will also be uploading a supplemental video for normalization to discuss and to illustrate more on database normalization. Thank you and good day.